All right, guys, I'm going to go ahead and get started with this podcast, which is on writing complete and net ionic equations. This is something that you're going to be doing throughout this entire course and in AP chemistry as well. So this is a critical skill, a critical concept for you to master. So we're going to be doing this a lot of times for double replacement reactions, but it can also be done for other types of reactions like single replacement reactions. And we're actually going to be doing this in some upcoming podcasts over oxidation reduction equations. So this is a very important podcast for you to follow along and make sure you understand. So we have been writing formula equations so far in this course. And in today's video, I'm going to teach you how to write a complete ionic equation and also a net ionic equation. Just a reminder that when we're specifically referring to double replacement reactions, these reactions involve the formation of a precipitate. Could be an acid-base neutralization reaction. Could also be the evolution of gas and gas formation from the subsequent decomposition of typically like carbonic acid is one that we've talked about already in this course. So here's a reaction that we looked at in an earlier podcast. Beautiful yellow precipitate. I'm sure by this point we've done this one in class. So it's a good starting point for us. So I have here the balanced formula equation for potassium iodide being mixed with lead 2 nitrate. And we get this beautiful yellow lead 2 iodide precipitate. And you can again determine that by using your solubility table or by becoming familiar with some of the solubility rules. Now, I have several examples in this podcast. This is just for you to sort of take it in, get some notes, and have a starting base point for subsequent equations. So basically what you're going to do is you're going to identify all soluble species. These are species that will ionize in an aqueous environment. And you're going to essentially show them in their dissociated form. All other species, such as solids, liquids, and gases, are going to remain in the same form as they were in your formula equations. So you're not going to, those do not ionize, those stay as a gas, a solid, or a liquid. One thing you may notice as you go across here is we are taking the subscripts here, and it's actually going to become a coefficient. Now, there are some critical pieces to writing these equations. For one, you want to always include states of matter. You want to always include charge. After all, these are called ionic equations or net ionic equation, and an ion is a charged species. So please don't forget the charge as superscripts. Please don't forget the states of matter. And as we go through and practice these, starting with a balanced formula equation, any of our subscripts will become coefficients. Okay, so here's our net end result, and you may be looking at this, and I want you to look at this and say, well, it looks like what you've done is you've canceled out ions that are common on both sides. And indeed, that is what has been done. Let's take a look at some examples here. Okay, so a definition for these guys that appear on both sides, those are known as spectator ions. Spectator ions. These are ions that are the same on both sides. They do not participate whatsoever in the chemistry. They are simply there. So we refer to them as spectator and we cross them out. And in our final product, which is our net ionic equation, we do not include spectators. Now, there are a couple terms that I'd like to discuss while we're on this topic of dissociating in an aqueous environment, ionizing, etc. And those are the topics or definitions for solvation and dissolution. Solvation is the process in which solvent molecules surround a solute. Now, to remind you, for example, this may be sodium chloride in water. When the sodium chloride is added to the water, the sodium cation dissociates from the chloride anion. All right, so what you're seeing here is this process of solvation. The solvent, i.e. the water, is surrounding the solute, i.e. the sodium cation. Now, they are very similar, but there is a difference between the two. Dissolution is the overall process in which a solute is dissolved into a solvent to form a solution. And this involves essentially breaking bonds of, say, water, breaking Coulombic attractions within sodium chloride, and then the new bonds forming between the water and the cation, or the water and the anion. And we're going to talk all about this in upcoming units, but it's a good time to kind of throw out that idea so you can see what we mean by the sodium cation, for example, ionizing or dissociating in water. Okay, sweetie, we'll go outside in just a little bit. Come say hi to the camera. Say hi to all of Daddy's students. Hi. Okay, now we'll go out in a little bit and we'll play, okay? Let Daddy finish this podcast, okay? All right.
I just got a picture set up.
Ooh, cool. Okay, so lots of examples here. That's how you get good at this. So we have ammonium sulfide being mixed with iron 3 sulfate. I've gone ahead and written out, we've had enough practice with this. You should be very proficient at writing out the formula equations. The purpose of this is to learn how to write complete and net ionic equations. So to save us a little time, I've already gone ahead and done that for all of these examples. Okay, so step number 2 here is we're going to look at our species that it will dissociate. Those are all the aqueous species. This guy here will not dissociate. Remember, liquids, solids, gases do not ionize. So now I'm going to go through this long process of turning this into its ionized form.
Dad, I still need to make the cookies for the picnic.
You make cookies, and as soon as you're done, we'll go outside and have a picnic. And Daddy's going to finish this, okay? Thank you, Sophia. Okay, so this subscript will become a coefficient. 2 NH4 states of matter. Very tedious, class. Very tedious. We're talking ions, so don't forget the charge. Plus sulfur. 2 minus aqueous plus my iron here. This was iron 2 plus aqueous plus SO4 2 minus aqueous. All right, so we have all of our reactants dissociated, and that's going to yield 2NH4 plus aqueous plus SO4 sulfate 2 minus aqueous. And now we get to leave our iron 2 sulfide in its solid form. We do not break this one up into its ions.
Can I please take a little picture of you?
Yes, you may take a picture of me, sweetheart. Okay. Now, the next thing we're...
Just look for outside.
Sophia, please, I have to finish this podcast, okay? And then I'll come play. Okay, now what we're going to do here is we're going to look for spectators. Who is on both sides? I see sulfate, sulfate, ammonia, ammonia. Okay, now I'm going to rewrite this into its net ionic form. So we have, and it doesn't matter what order I write these in. And that's going to yield my precipitate. So this is showing what's actually occurring when these compounds are mixed. This is your net ionic equation for this particular example. Better late than never. I guess I should also mention that you may want to use your solubility table throughout this podcast to determine which are solids and which are aqueous species. Okay. All right. Example 2. And so if you're feeling it, pause it and try it on your own. Try to do a complete and then try to do your net ionic equation. I'm going to go ahead and get started. And so copper 2 plus aqueous plus my sulfate. Don't forget states of matter. Don't forget charge. Plus calcium, that's a 2 plus. These are aqueous. Plus sulfur, 2 minus. Aqueous yields. Now, I chose this one because it's pretty cool. These are not common, and they occur in very dilute solutions when they're in low concentrations. This is a double precipitation, double replacement reaction. That's a mouthful right there. So I am not going to break up either of these. They're both precipitates, all right? So when you go through and you look for spectators, you don't have any. You don't have any because every one of these species is participating in this double precipitation reaction. Pretty cool. Not very common, but they do exist, so worth mentioning for sure. All right, next example, strong acids. This is a neutralization reaction. When we mix a strong acid and a strong base, we get salt water every time. So one thing that you're going to learn is that strong acids and strong bases completely dissociate into their ions. That's a whole other beast of a unit we'll tackle later, but I'm throwing that out there, and I've already thrown that out there in a prior video as well. So let me go ahead and break this guy up here. We have 2 hydrogens. We have 2 nitrate anions. We have strontium, which is a group 2. And we have 2 subscripts become coefficients, hydroxide anions, aqueous. And that is going to yield, I'm running out of room, so I'll go over here. The strontium, 2 plus aqueous, plus the nitrates. And there's 2 of those guys. And you're probably remembering, I hope, that all nitrates are soluble, are aqueous. And then we have our water here. So 2H2O liquid. This does not ionize. This stays in its molecular form as water. Let's eliminate spectators here. Nitrate, nitrate, strontium, strontium. And so what we end up with is, this is pretty cool. H plus 2OH minus yields 2H2O liquid. And yes, we can eliminate these coefficients and simplify this. Not sure if I really need to write it out, but I'm all in at this point. Aqueous, and in its simplified final form, what are we showing here? that a proton and a hydroxide anion, when they come together, they form water. All right, example number 4. This is a single replacement reaction. And we're going to be using these in some of our upcoming podcasts to balance what are called redox reactions. This is a method that works for here as well. So we're going to take solid lithium metal, a group 1 metal, and we're going to put it into liquid water. And a very violent reaction will occur, giving a strong base called lithium hydroxide and hydrogen gas, which is explosive. So this is an exothermic reaction. And so I like it because it's a little different, but we can still write a net ionic equation for this. So we're going to leave the lithium. We are going to leave the water. We're going to dissociate the lithium hydroxide. So 2Li plus, and that's aqueous, plus 2OH, aqueous, plus gas. We don't mess with the gas, we leave it alone. And are there any spectators around? There are no spectators, but this is the ionic equation for this particular reaction. And what it's showing essentially is when this solid material is placed in the water, when the reaction is complete, the lithium and hydroxide have ionized. You won't really be able to, you won't see what happened to the lithium, what happened to the metal. Well, it's gone into its ionized, dissociated form. Now it's going to create a solution that is basic, and it's going to evolve this hydrogen gas. And our last example, we have one of those where we're forming a carbonic acid, which will subsequently break down into H2O liquid and carbon dioxide gas. So I've gone ahead, we've done similar examples, so let's pick it up right here with this guy. All right, here we go. So I am not going to dissociate these compounds. Everything else is aqueous, everything else is dissociated. Subscripts become coefficients. Don't forget charge and states of matter throughout. So let's see if we can knock this thing out here as quickly as possible and wrap up this podcast. 2 strong acid completely dissociates. Stay tuned on that. Chloride anion, aqueous 2 yields 2 potassium cations plus 2 chloride anions plus, better continue over here, H2O and carbon dioxide gas. All right, spectator time. Potassium carbonate. No carbonate. These protons here, no. How about these 2 chloride anions? Spectator. Let's go ahead and write our final net formula. This is so cool. Plus 2 yields H2O plus CO2 gas. And that's it right there. That's our net ionic equation for our final example of this podcast. Now, I do want to make sure I make a point here. For our Georgia Standards of Excellence today, we've hit a couple different ones. We talked about dissolving in terms of solvation and dissolution. Remember, solvation is that process by which the solvent surrounds the solute, and dissolution is the overall process of the compound being dissolved into an aqueous solution. We've also continued our standard looking at mathematics and computational thinking to balance chemical reactions. And we have here a problem set that you're going to get lots of practice on, writing and balancing both complete and net ionic equations. I'll see you in class. Thanks.